A coastal wetland can survive rising water for years while appearing almost unchanged. Then the sea rises slightly faster, and the landscape begins disappearing at nearly 8 times its previous rate. New global research suggests that this abrupt shift happens around a specific number, 9 millimeters of relative sea level rise per year. Below that threshold, many salt marshes and mangrove forests can still adjust. Beyond it, the probability of rapidly accelerating loss rises above 92%. This is not simply a story about plants being covered by water. Tidal wetlands are living landscapes positioned between land and sea. They absorb waves, reduce erosion, provide nurseries for fish, store carbon in waterlogged soil, and create a natural buffer between coastal communities and storms. The new finding suggests that these systems may not decline gradually as sea level rises. Instead, they can approach a tipping point, cross it, and begin collapsing much faster than expected. The study examined salt marshes and mangroves around the world using several sources of satellite and coastal data spanning roughly 2 decades. The researchers compared changes in wetland area with relative sea level rise, which describes how fast the ocean is rising compared with the nearby land. That distinction is important because a coastline can experience rising water for 2 different reasons. The ocean itself may be getting higher, or the land may be sinking beneath it. Imagine standing in a slowly filling bathtub while the floor beneath you is also moving downward. From your perspective, the water climbs faster than either process would suggest alone. Coastal wetlands experience the same combined pressure. Melting glaciers and ice sheets add water to the ocean, warming seawater expands, and in some regions groundwater extraction, sediment compaction, or geological movement causes the land to sink. NASA's satellite record shows that global mean sea level has risen by more than 10 centimeters since 1993. The global average does not describe every coastline, however. Local changes can be much faster or slower because land movement, ocean circulation, and regional ice loss patterns alter what individual shores experience. Wetlands are not completely helpless against this rise. A healthy salt marsh can trap mud and organic material between its stems. As sediment accumulates, the surface of the marsh grows vertically. Mangrove roots perform a similar function, slowing water, trapping particles, and building soil. In the right conditions, the landscape can gradually lift itself as the sea rises around it. Wetlands also have another escape route. They can move inland. As salt water reaches higher ground, marsh plants and mangrove seedlings may colonize new territory behind the existing shoreline. The seaward edge may erode while a new wetland forms farther inland. Viewed from above, the ecosystem appears to migrate rather than simply vanish. But both survival strategies have limits. A wetland can only build upward if enough sediment and organic material arrive. Dams may trap river sediment before it reaches the coast. Channels and seawalls may redirect water. Erosion may remove material faster than plants can capture it. If the sea rises faster than the surface can grow, flooding becomes deeper and lasts longer. Plant roots receive less oxygen, vegetation weakens, and the mud becomes increasingly vulnerable to waves. Moving inland can be even more difficult. Roads, farms, buildings, levees, and concrete seawalls often occupy the higher land behind the wetland. The ecosystem becomes trapped between advancing water and fixed human development. Scientists call this coastal squeeze. The wetland cannot remain where it is, but it has nowhere else to go. The new study found that these pressures do not produce one smooth, predictable response. Instead, wetland loss accelerates nonlinearly as relative sea level rise increases. Around 9 millimeters per year, the behavior changes sharply. Above this point, the measured rate of wetland loss becomes roughly 8 times greater, and the probability that loss is accelerating exceeds 92%. 9 millimeters sounds insignificant. It is less than the width of a human finger. But that small annual rise repeats year after year, while tides and storms repeatedly push water across the same landscape. In 10 years, it approaches 9 centimeters. More importantly, the wetland must constantly add material, maintain healthy vegetation, and reorganize its channels merely to keep its surface in the same position relative to the sea. A system that falls behind does not simply pause. Once plants begin dying, their ability to trap sediment declines. With fewer roots holding the soil together, erosion increases. As the surface drops or breaks apart, water penetrates farther inland and remains for longer. The wetland loses the biological machinery that previously allowed it to resist the rising sea. This creates a feedback loop. More flooding damages vegetation. Less vegetation captures less sediment. The surface fails to build upward. Deeper flooding causes additional vegetation loss. A landscape that once defended itself can begin helping its own collapse. The researchers also found an important difference between salt marshes and mangroves before the threshold is reached. Salt marshes tended to show modest, progressive losses as sea level rise increased. Mangroves appeared comparatively stable for longer, but once the threshold was crossed, their losses also accelerated abruptly. That contrast matters because a stable-looking mangrove forest may not necessarily be safe. It may be absorbing stress without displaying dramatic area loss, then change rapidly after environmental limits are exceeded. This is similar to bending a branch. For a while it flexes and appears resilient. But resilience does not mean unlimited strength. Once the breaking point is reached, the final change can happen quickly. The study also examined lateral wetland movement, including erosion along one edge and expansion elsewhere. This ability provided some buffering, but only a limited amount. The threshold associated with lateral change was only slightly different from the threshold for direct drowning. Tidal range and sediment supply influenced how effectively wetlands adjusted, but migration alone could not guarantee survival under increasingly rapid sea level rise. This challenges a comforting assumption. Coastal wetlands are sometimes portrayed as ecosystems that will simply move inland as the ocean rises. In reality, migration requires open space, suitable elevation, compatible soil, sediment, and enough time for vegetation to establish. A forest, highway, city, or steep hillside can stop the process completely. The discovery is significant because tidal wetlands are more than wildlife habitats. They are physical infrastructure built by living organisms. During storms, dense vegetation slows moving water and reduces wave energy. Roots stabilize sediment. Channels spread floodwater across a wide surface rather than concentrating it against a single shoreline. When wetlands disappear, the water does not disappear with them. Waves travel farther toward roads, homes, farms, and seawalls. Storm surges reach areas that were previously protected. Coastal erosion can accelerate because the shore has lost one of its natural shock absorbers. Wetland soils also store large amounts of carbon. Waterlogged ground slows decomposition, allowing dead roots and organic matter to accumulate for decades or centuries. When wetlands erode or drain, some of that stored carbon may return to the atmosphere or surrounding water. A disappearing wetland therefore represents both an adaptation problem and a potential climate feedback. A separate global analysis published days after the threshold study estimated that tidal wetland soil organic carbon declined by just over 6% during approximately 1 decade, with major losses occurring in deeper soil layers and mangrove regions. Together, these findings show that a wetland can lose ecological value below the surface even before every visible plant has disappeared. The 9 millimeter threshold should not be treated as an exact deadline for every wetland. Real coastlines differ enormously. A sediment-rich river delta may respond differently from a small island marsh. A mangrove forest with room to migrate may survive longer than one surrounded by buildings. Storms, pollution, plant species, tidal range, and human engineering all affect the outcome. The study provides an observed global benchmark, not a universal switch that activates identically everywhere. It identifies the point where the risk of accelerating loss increases sharply across the combined data. Local monitoring is still necessary to determine how close any particular wetland may be to its own limit. But the threshold offers coastal planners something they previously lacked: a measurable warning sign. Instead of assuming gradual change, managers can identify regions where relative sea level rise is approaching dangerous rates. They can then prioritize sediment restoration, reconnect rivers to floodplains, remove barriers to inland migration, or protect undeveloped land behind existing wetlands. In some locations, allowing controlled flooding of low-lying land may create future habitat. In others, restoring natural sediment flows could help wetland surfaces rise. Setback zones can prevent new buildings from blocking migration routes. These actions cannot stop the ocean from rising, but they may determine whether a wetland has space and material to adapt. The broader lesson is that environmental change is often not linear. A coastline may appear stable while its safety margin quietly narrows. Then one additional millimeter of annual rise, one lost sediment source, or one new seawall can push the system into a different state. For years, coastal wetlands have been described as resilient ecosystems capable of growing with the sea. That remains true, but only within limits. They need sediment, vegetation, space, and time. Remove any of those, and rising water begins winning the race. Scientists have now identified where that race changes dramatically on a global scale. Around 9 millimeters per year, the wetland's slow struggle can become rapid retreat. A number smaller than a fingernail may separate a coastline that adapts from one that begins to disappear.